So in this video we're going to answer the age-old question of which integration method should you use? I get asked this question a lot from my students and online, so let's get into it. So the first question we should ask ourselves is it basic? Is it of the form of x to the power of n, where n is not equal to minus 1? So for example, x squared. We can add 1 to the power, divide by the new power, x cubed over 3. If it's x to the minus 3, again, add 1 to the power, divide by the new power, x to the minus 2 over minus 2, plus c. Sometimes you might have to do something to it first. It might be written as the square root of x, for example. So we can write that as x to the half, and then add 1 to the power, divide by the new power. Or 1 over the cube root of x is the integral of x to the power of minus a third. Again, add 1 to the power, divide by the new power. If you have a single term of x in the denominator, then it's likely that you can simplify the fraction. Okay, so we're in a case of here where you can write that as the integral of x squared over x squared, which is 1, and then plus 2 over x squared, which is 2x to the minus 2. So split it up into two terms, x squared over x squared and 2 over x squared. Likewise, here we have x to the half divided by x, which is x to the power of minus a half. And then we've got 3x cubed over x, which is 3x squared. And then you integrate. So you have to prepare them first. Okay? So in each of these cases, you're just going to be adding 1 to the power divided by the new power, right? Of course, 1 integrates to x, and then just make sure you're adding on your constant of integration. Now the next question is it a standard function? So if we have the integral of e to the x, we should recognise that that just integrates to e to the x plus a constant c. Sin x integrates to minus cosine plus c, and cosine x integrates to sin x plus c. So in the order of integration differentiation with sine and cosine, it goes sine, cosine, minus cosine. Differentiating your way down, integrating your way back up. So if that helps you remember, that's what you need to use. The one that quite often people forget is the integral of 2 to the x, which is 1 over the natural log of 2 to the x, plus a constant c. So if you've got 3 to the x, that's 1 over log 3 to the x, plus c, 4 to the x, 1 over log 4 to the x plus c, etc. So that's the rule of how you integrate 2 to the x, or a to the x. 1 over x, now we're going back into the territory of is it basic, but now you've got x to the minus 1. So it doesn't follow the same rule. You can't write that as x to the minus 1 and then add 1 to the power and divide by the new power. It's the one scenario that breaks the previous examples. So 1 over x integrates to the natural logarithm of the modulus of x plus c. Now this one looks very similar to what we had in the previous selection of questions. Now we've got root x plus 3 over x. Again, you want to make sure that you can break this apart. So we've got root x over x. X to the half over x is x to the minus a half. So we've got the integral of x to the minus a half. And then plus 3 over x. Now, of course, you can write that as 3x to the minus 1 if you like. But then when you're adding 1 to the power dividing by the new power, this integrates in a basic, because it is a basic integral, x to the minus a half, add 1 to the power, you get a half, divide by a half, you get 2, so 2x to the half, and 3 over x integrates to 3 natural log of the modulus of x plus c. Okay, so because that's 3 lots of 1 over x. So 3 lots of this, 3 lots of the natural log of mod x plus c. Okay, Now we can modify these slightly to have e to the kx or e to the 2x, e to the 3x, e to the 4x, sine of 3x, cosine of 5x. So here you are now reversing the chain rule, but I always like to think about this as you're just remember these as standard integrals. So if it's e to the kx, then that's 1 over k e to the kx plus c. And sine of kx, well, you introduce that 1 over k out in front, just like you have for this example. Sine integrates to minus cosine, okay? So we need to go minus 1 over k cosine of kx plus c. Cosine of kx, again, 1 over k, sine of kx plus c. Now the next question is it in the formula booklet? Now, if you look in your formula booklet, regardless of whether you're doing AQA, Edexcel, OCR-A or OCR-B MEI, you have in your formula booklet a little table that probably says differentiation. So it shows you how tan, sec, cot and cosec differentiate. Now, because you know how they differentiate, that also means you know how these integrate. Okay, so these are the answers to that. So we can reverse the process. So if you've got an integral of sec squared x, you should know that that is tan of x plus some constant c. If you've got an integral of cosec cot x, okay, now in the formula booklet it says cosec differentiates to minus cosec cot. So cosec cot must integrate to minus cosec. Okay. Sec tan, well, sec differentiates to sec tan, so sec tan must integrate to sec. And lastly, we know that cot differentiates to minus cosec squared, so cosec squared must integrate to minus cot x plus c. Now likewise, just as we had with the trig from before, we could have sec squared of kx, so sec squared of 2x, sec squared of 3x, and so on. And so this is going to integrate to 1 over k, just like we had before with e to the kx, sine of kx. So we have 1 over k coming outside, tan kx plus c. Okay? So here we've got cosec of kx, cot of kx. Now, we know that if it's just cosec x, cot x, it integrates to minus cosec x. So here we've got the kx involved, so we're going to have 1 over k out the front, so minus 1 over k cosec of kx plus c. Now, quite often people think that there should be minus 1 over k squared out the front here, okay, because you've got the kx and the kx, and so they think there's going to be both coming out. But if you reverse the process and you differentiate this using the chain rule, the derivative of the inside comes outside, so that's k, comes outside and multiplies with a 1 over k, so you get minus 1 out the front. And then we know that cosec differentiates to cosec cot, okay, so minus cosec cot, so that knocks out the minus sign, and then the inside stays the same. So the kx, kx. And so you don't get that two lots of 1 over k coming out the front and becoming 1 over k squared. It's just the singular. Likewise, for sec kx, tan kx, this is going to integrate to just 1 over k sec of kx plus c. And cosec squared kx, well, we know that cot differentiates to minus cosec squared, so reversing the process, we will have minus 1 over k cot kx plus c. Now there's a few of these that I would refer to as reversing the chain rule, and I've already mentioned that in a couple of these other ones here. So when we talk about standard functions, or was it in the formula booklet? So reversing the chain rule does encompass a great number of examples, and I've still got a couple more that are essentially reversing the chain rule, but we kind of like to think of it more as just like something that you spot, more so than if it's something that looks like this. I always think of these distinctly as reversing the chain rule questions. So integral of x plus 1 to the 5, integral of 2x minus 3 to the 6, integral of square root of 8x minus 1. So the way that I like to do these, okay, because I don't really like to do them much in my head, but you can get good at them if you do practice them, is to think about the format that you are going to arrive at. So I know that I'm going to get an x plus 1 to the 6, okay, something x plus 1 to the 6 from integrating this. So what I do is I imagine what would I get if I had x plus 1 to the 6. So I add 1 to the power and then think about differentiating it. Well, what would happen is the derivative of the inside is 1, that comes outside. The power comes down to the front and I take 1 from the power. So what I get here, if I reverse the process, is 1 over this coefficient. So 1 over 6. So just like you were getting this 1 over k in previous examples, this is the same idea. We're getting this 1 over 6, x plus 1 to the 6 plus c. So if you try that process with this next one, then we think that we're going to get 2x take away 3 to the 7, right? We add 1 to the power. We differentiate that. So the derivative of the inside is 2, that comes outside, and the 7 comes down to the front. So we've got the 2 out there already, multiplied by the 7 gets me 14, 2x take away 3 to the 6, and then we do 1 over this number. So 1 over 14 comes out the front, 2x take away 3 to the 7 plus c. So again, as I said, you may get good at doing this without having to write this line down, okay? So imagine adding 1 to the power, differentiating it, whatever you're getting out the front, it's 1 over that, okay? So if we tried it with this one, then first thing to recognise is that you've got 8x take away 1 to the half, right? So first of all, write it in a format like that. If you add 1 to the power, you're going to get 3 halves, okay? The derivative of the inside comes outside, so you'll have 8 multiplied by 3 halves. So 8 times 3 is 24, divided by 2 is 12. So you get this 12. So it's 1 over 12 that should come out the front. 8x take away 1 to the 3 halves plus c. Okay? So, of course, you can double check that. So let's just quickly double check it. So imagine adding 1 to the power, differentiating this. So you can have 8 multiplied by 3 halves. So 8 divided by 2 is 4, times by 3 is 12, or 8 times 3 is 24 divided by 2, which is 12. 8x take away 1 to the half, and it's 1 over that number. Okay? So all's good. So that's how you can reverse the chain rule and integrate things like this quickly. Now I should say, don't forget that any of these can be done by integration by substitution as well. Okay, any that are reversing the chain rule, we can do by substitution. It's just going to take you longer and more steps. If you can do an integral like this in one line, then that obviously speeds you up in the exam. Now the next thing to check is it f prime over f? Now, I always try and get my students to think about, if it's a fraction, the first thing that you should check is, does the bottom differentiate to the top, or a multiple of the top? Okay, so we've already met this before, 1 over x. It's a fraction though. Does the bottom differentiate to the top? X differentiates to 1, so yes. So this is the natural logarithm of the modulus of the denominator plus c. So the rule is that this integrates to the natural log of the modulus of the denominator plus c. This is another process of reversing the chain rule, okay? Because if you start with that, to differentiate it, you use the chain rule and you get to f prime over f. So this is a process of reversing it. So this one, 1 over x plus 1, the bottom differentiates to 1. So this just integrates to the natural log of the modulus of the denominator plus c. This one, 3x take away 5, differentiates to 3. So this integrates to the natural logarithm of the modulus of 3x take away 5 plus c. Now what about this one? The bottom differentiates to 2, and on the top you've got 3. Okay? So the way you deal with that is you go, okay, well, what I'm going to end up doing is get the numerator and divide it by the derivative of the denominator. So you do 3 divided by 2, and that's what comes out the front. So 3 halves times the natural logarithm of the modulus of 2x plus 7 plus c. Now, why does that happen? Why does that work? Well, the idea here is that if you considered dividing this by 2, so if you take the factor of 2 out, for example, so let's write that as, well actually let's factor out the 3 rather. So if you write that as 3 lots of the integral of 1 over 2x plus 7 dx, okay? I can do that, that multiply of the 3, I could bring that out the integral, it doesn't make any difference. Then what I could do is I could multiply this fraction top and bottom by 2. So imagine multiplying that fraction top and bottom by 2, you're going to get 2 on the top and 2 lots of 2x plus 7 on the bottom. Okay? But again, just like I factored the 3 out of the integral, I can factor that 2 out of the denominator and bring the half out the front. So I'd have 3 halves times the integral of 2 over 2x plus 7 dx. Now that by itself just integrates to the natural logarithm of the modulus of 2x plus 7. And you've got this multiplier of the 3 halves out the front. So multiply that by 3 halves. So that's why we could go straight from this to this. If you do your bottom, differentiate it, you get 2, 3 over 2, that's going out the front. Okay? Actually, I'll leave that for the moment. Let's look at this one. X over 2x squared plus 3. Again, fraction. Does the bottom differentiate to the top? Well, the bottom differentiates to 4x, and we've got x on the top, so not quite. So if we use a similar idea here, and we go, okay, well what we do is we divide the x by the derivative of the bottom. So x divided by 4x is a quarter. And that's what comes out the front. 1/4 times the natural logarithm of the modulus of 2x squared plus 3 plus c. Now, theoretically, you might be going, well, we don't really need the modulus because this will always be positive. Fine, you won't get penalised for having the modulus there, okay? And it's a good way just to kind of like just keep it in there to remind you. Now, depending on your exam board, you may or may not have the integrals of tan, cot, cosec and sec in your formula booklet. If you are OCR A or OCR B, you don't have any of these. If you are AQA, then you have those 2. If you're Edexcel, you have all 4. Now, the integral of tan and cot, you don't really need to have them in the formula booklet, because the idea is that the integral of tan is the same as the integral of sine over cosine. And of course that's a fraction, so you should check whether the bottom differentiates to the top. Now cosine differentiates to minus sine, so that means that we have minus the natural logarithm of the modulus of cosine x plus c. Now a lot of people, what they do is they then bring this minus sign up to the power using your log rule. So you can write that as log of 1 over cosine x, which is log of sec x. Okay, so in your formula booklet you'll find it as log of the modulus of sec. The same thing with cot. So cot is the integral of cosine over sine. It's a fraction, so check whether the bottom differentiates to the top. Sine x differentiates to cosine x, so this is the natural logarithm of the modulus of sine x plus c. Okay? Now, as for these two, I have done a video on how you get to these answers, but cosec is the integrates to minus the natural log of the modulus of cosec plus cot x plus c, and sec integrates to the natural log of the modulus of sec x plus tan x plus c. Okay? I would anticipate that if they were to be used in the exam, then they're going to be used in Excel. So it's likely you would just have to use those results, okay, that are in the formula booklet. So keep an eye out for those. Now, all of the times that we've been using this rule here, we've done it with x's in the numerator denominator, so polynomial over polynomial. We've done it with some trig. But what about other functions? It could be, well, it could be another function. So it could be something like e to the x. Now, I've written these two down because they're both fractions. So the first thing you should check is, does the bottom differentiate to the top? So with this case, e to the x plus 1 differentiates to e to the x. So that means we can use our rule here. This is equal to the natural logarithm of the modulus of e to the x plus 1 plus c. And no, before anyone asks, you can't simplify that. Okay? You can't break the logarithm apart because you've got the addition inside the logarithm. It's not a multiplication. Okay? So that's our answer for that one. But this one, which looks awfully similar, I've just done the reciprocal, does the bottom differentiate to the top? No. E to the x doesn't differentiate to e to the x plus 1. This is going back to, is it a basic? Because this one you can split up into e to the x over e to the x, which is 1, plus 1 over e to the x, so e to the minus x. So we get x, and then e to the minus x will integrate to minus e to the minus x, plus some constant c. Okay? So two very similar looking integrals, but different methods. But wait, there's more. Reversing the chain rule. Okay, so there's also integrals that are of this structural form, f prime times f to the n. Now the idea here is that what you're looking at is, look for that interior function, so x squared plus 1, e to the x plus 3, sine x, cosine x. The one that is inside a bracket to the power of. So here, this is sine x, so you could write that as the integral of cosine x, sine x to the 5, right? Like you could write this one as the integral of sine x, cosine x cubed. So the interior function, the one that is to the power of, okay? If you differentiate that, is there a multiple of that at the front? So x squared plus 1 differentiates to 2x. You've got x out the front. So you've got a multiple of it out the front. So this is also reversing the chain rule. And the way that I tackle these, you could again do these by substitution, right? Alternatively, you can think of this in the same way as we reversed the chain rule before. So if you go back to when we did this bit, right at the start, if you differentiate what you're expecting to find, so we think it's going to be x squared plus 1 to the 5, some multiple of this. You differentiate that. The derivative of the inside is 2x. The 5 comes down to the front. So we're going to have 10x, x squared plus 1 to the 4. Okay? That's what that differentiates to. So, what happens to integrate that? Well, we're going to have 1 over this coefficient. 1 over 10. X squared plus 1 to the 5 plus c. And that's how we can integrate it in one line. Okay? So, this one, e to the x plus 3 is the interior function. That differentiates to e to the x. So imagine having e to the x plus 3 to the 6. You've added 1 to the power. What does that differentiate to? Well, the derivative of the inside comes outside. That's e to the x. The 6 will come down to the front. And we're going to take 1 from the power. So what do we get from this? 1 over 6 e to the x plus 3 to the 6 plus c. Okay? So lots of people kind of like look at these types of integrals and go, oh, no, I can't do it. I must do it by substitution. These can be done in one line, just like those from before. They do look meaner, right? I do agree with that. Just like these, okay? These do look meaner, right? But imagine adding 1 to the power of the sin x and having sin x to the 6. What does that differentiate to? Well, the 6 is going to come down to the front. The derivative of the inside comes outside, so that's cosine x. And we're going to take 1 from the power. So we're going to have 1 over 6 come out the front. So this is 1 over 6 sine to the 6 x plus c. Shall we try and do it, this one, but in the one step? So we're thinking it's going to be cosine x to the 4. Differentiate that. We're going to have the derivative of cosine is minus sine, and the 4 comes down to the front. So we have minus 4 sine of cosine x squared. Cosine x cubed, rather. Apologies. But maybe I should have written it out. Maybe I should write it out. Let's not rely on it. I was almost there. Almost there in my brain. Let's write it out. Let's walk before we can run. So, add 1 to the power. Differentiate this. The derivative of the inside comes outside. That's minus sine. The 4 is going to come down to the front. And we're going to take 1 from the power. I said squared, it was cubed, wasn't it? Okay? So, what are we going to have? We're going to have 1 over this. So, minus a quarter cosine to the 4x plus c. Okay? Right, then we get to integration by substitution. Now, integration by substitution is going to fall into 2 different categories. There are either going to be questions where it says, use the substitution, in which case there's really not much choosing of integration method there, okay? They've told you what they want you to use, and they've told you the substitution they want you to use, okay? So it's either going to be that, or there's going to be an integral that requires the use of integration by substitution, And that's because you've identified it as having failed all the previous methods that we have. So, for example, if we look at this one, this looks somewhat similar to this, but the derivative of x take away 3, the interior function, isn't a multiple of x plus 1. So we can't use that. Likewise, this one, similar vein, this differentiates to 4, which isn't a multiple of 2x take away 5. This one, you might be thinking, oh, it's a fraction. Does the bottom differentiate to the top? X take away 3 differentiates to 1. That's not the top, or a multiple of the top. So that's out, okay? Same here. That doesn't work either. Bottom doesn't differentiate to the top. Bottom doesn't differentiate to the top, okay? So, if all of our previous methods fail, integration by substitution is going to be the next thing that we might look at. And also, it may well be the case that some of these can also be done by parts. So, for example, this one and this one you could alternatively do by integration by parts. If you're using integration by parts, you would choose u to be x plus 1, u to be 2x take away 5. Okay? If you're doing that, you'll end up reversing the chain rule twice. You have to do reversing the chain rule twice. It's a bit more messy, I would say. I would probably stick to integration by substitution for these. So, in the grand scheme of things, right, it's not that integration by substitution and integration by parts are mutually exclusive. So, in the Venn diagram of integration methods, substitution and parts do have a bit of an overlap. Okay, there are questions where you could theoretically do either, and these are examples of that. So, if I was using substitution, what substitution would I use? Well, I would use this, the interior function that's to the power of the bigger number, right? So this is the power of 1, this is the power of 8, this is the one to choose. So use u is equal to x take away 3. Now I'm not going to go through how integration by substitution works. I've got lots of videos on that. So I won't go through the process, but always make sure that your first step is differentiate your substitution. So next thing would be find du by dx. Okay? So here, again, I've got 2x take away 5 to the 1, 4x plus 3 to the 6. Choose the one that's to the higher power as the u, so u is equal to 4x plus 3. Now, this one, if it's a fraction, like this, there are alternative methods to substitution as well. If you were going to do it by substitution, I would use u is equal to x take away 3. So use the denominator as your substitution. Okay? That's really key to this. But this one does have alternative methods. You could use polynomial division first to divide 5x plus 2 by x take away 3, and then integrate it. I'll show you how that works in a moment, okay? But there is that alternative method. You could also do it by, there is a method of inspection here as well, of being able to simplify it into, replace it into 2 terms essentially, rather than just have the one, which the polynomial division will do. I don't like to rely on just doing it by spotting it. I find that quite difficult to do. So, you know, we can't be good at everything, I'm afraid. So that's something that in my brain I just cannot kind of like spot. So I always use polynomial division. I'll show you what I mean in a moment. This one, polynomial division, no way. You've got that square root in the bottom, okay? That's causing a problem. You can't go about it that way. However, substitution will work. again, I would choose u is equal to x plus 2. That would be my personal choice. However, you could alternatively use u is equal to the square root of x plus 2. Now, the only reason as to why I personally wouldn't choose that is because this is invariably harder because you've got some differentiation involved with using the chain rule. I think in the majority, people probably find that easier, but I have seen exam questions in the past which have given something like that and have asked people to use this substitution specifically, which I think is a bit of a nuisance, but there you go. This one, if it's something like this, this is one where you would be given the substitution. Okay, so there are some integration by substitution ones, particularly ones with trig replacements, where you will be given the substitution. So this one, you can use cosec of u, rather. Okay, don't know why I wrote the u like that. There we go. Cosec of u, and that will work fine. Memory serves, I think there is another substitution that you could use for this one as well. But this came up like over 10 years ago now in an old exam paper. So x equals cosec u was the substitution given for that. I think it was back in, it was one of the AQA papers from 2012. I think it was January 2012. And it would have been core 3, I think. Core 3 or core 4. I think it was core 3. Okay. Right. Enough of that rambling on. Let's get back to this one. Okay. So, if I was wanting to use not substitution for this, and I wanted to rewrite it in a format where I could integrate it straight off the bat, I would use polynomial division. So the way to do that is to write x take away 3 down the side. We're going to divide 5x plus 2 by x take away 3. Now, if you want to do this by long division, be my guest, but I've totally gone over to the grid method here for polynomial division. So we want 5x, don't we? Okay, so if this is a multiplication grid, then I'm going to have x times 5 to make the 5x. 5 times minus 3 is minus 15. But I don't want 5x take away 15, I want 5x plus 2. So I'm going to have to add 17 onto that, and that will get me the 5x plus 2. So I can write this integral as 5 plus 17 over x take away 3 dx. So this is the remainder, the bit that wouldn't divide by x take away 3. So I've replaced this with this, and now I can just integrate that. 5 integrates to 5x, and this can be integrated using this, because it's a fraction. The bottom differentiates to 1. We've got 17 on the top, so this will be 17 lots of the natural logarithm of the modulus of x take away 3 plus c. Okay, and that shortcuts all of the integration by substitution. Right, now we move on to integration by parts. And each of these are kind of the archetypal integration by parts questions. So x e to the x sine x cosine x squared e to the x squared sine x squared cosine x log x, and log x by itself. So obviously there is a bit of a pattern here. You're seeing x times one of the standard functions. So x e to the x sine x cosine x, x log x, x squared e to the x squared sine x squared cosine x. All of those would be integration by parts twice. Okay, you're only ever going to need to do integration by parts twice, so it's up to a maximum 2. If I change this to x squared log x, that's still only integration by parts once. Okay, so if it's x squared e to the x squared sine x squared cosine x, these are all parts twice, but x squared log x is once. The reason why that is different is because it's a different choice of u. So remember, at the start of integration by parts, you need to identify what is u and what is dv by dx. Okay, so in order to do that, you're looking at the late rule. So this determines which u you should choose. So is it a logarithm? If not, right, that's out. Next you pick algebra. If there's no algebra, that's out. Next you pick trig, etc. Okay? So in our first example, we have no logarithms, so we're going to pick algebra, and that's the x. So u is equal to x, and dv by dx is the other bit, e to the x. Likewise here, u is equal to x, dv by dx is sine x. So algebra gets picked first over trig. Algebra gets picked first over trig. Algebra gets picked first over trig. Well, over exponentials rather. Okay? And the reason why this is going to go through two steps, two cranks of the handle of integration by parts, is because the u is x squared. And what happens is that each time you crank the handle, the integral gets simpler. So you differentiate it, you're going to get 2x, but you're still going to end up with an x e to the x inside your integral, so you've got to crank the handle again, and then you get down to e to the x. Okay? Whereas here, because you've got a logarithm, that gets picked as the u. So u is natural log of x, and dv by dx is x squared. Okay, so in this case, when you differentiate the log x, you get 1 over x. That multiplies with an x cubed when you've integrated that bit, and you end up with, what do you get? You get u times v. So you get log x times an x cubed bit, rather, and then you get v times du by dx. So, yeah, you'll end up with x squared inside the integral, won't you? Okay? So, which can then be integrated. So you only need to do that once. Now this last one, integral of log x dx, the trick is to remember to write that as 1 times log x. Okay, so by writing log x as 1 times log x, you can then say, okay, well, u must therefore be log x, and dv by dx is equal to the 1. So using the late rule, the log x is your log, and the algebra is the 1. Okay, so the algebra doesn't get picked as u, and so that has to be the dv by dx. Now you might still be going, well, but how do I identify its integration by parts? Well, I've kind of said that there are these archetypal ones that you should be able to spot off straight off the shelf. X e to the x, or x e to the 2x, or x sine 3x, or x cosine 5x, or something like that, okay? They're not integration by substitution because the interior function doesn't differentiate to a multiple of what you've got out the front. Okay? X sine x, x doesn't differentiate to x. Okay? But I could change some of these quite easily to something that is reversing the chain rule or substitution, right? So this thing here, right, well really, let's write it like this. So let's write this as x e to the x squared, okay? Let's say we've got this instead. We've got a function that looks very similar to it. Is that integration by parts? Well, it's not integration by parts for one main fundamental reason. It's not integration by parts because when you do your late rule, you're going to get u is equal to x, and dv by dx is e to the x squared. And as part of integration by parts, you differentiate this one, and then you've got to integrate this one. And e to the x squared cannot be integrated. So you run into a brick wall here. Okay, you cannot integrate e to the x squared analytically. There is no standard function that it integrates to. You can't write that. And so this method breaks for this example. But actually, you know, what have you got instead? Well, the thing is that x squared differentiates to 2x. And you've got a multiple of 2x out the front, okay? So methodology-wise, actually, this can be done by reversing the chain rule, right? This is another reversing the chain rule problem. So imagine that you are differentiating. Well, we would expect to get e to the x squared, right? Because I know that e integrates to itself. So imagine differentiating e to the x squared. So what would happen is the derivative of the inside comes outside. E differentiates to itself and the interior function stays the same. So using the chain rule. So we've got this extra coefficient of 2 out the front. And so this integrates to 1/2 e to the x squared dx. Okay? So essentially, what are we asking for here? Well, is it reversing the chain rule? So is it the integral of g prime f prime of g of x dx? Let's give myself a little bit of space. Okay, so is it that? So where you're going, right, I've got this interior function g of x that differentiates to g prime. Do I have the derivative of the interior function on the outside? And in this case, we do. So another example would be, let's modify that one. Let's say I had x sine of x squared dx. Can you do that by parts? Well, no. The reason is that you're going to have this problem, okay, and then dv by dx will be sine of x squared, and sine of x squared we can't integrate. And so it breaks at the same stage where we had before. So, oh dear, okay, can't go any further with that. So, in integrating x sine of x squared, the way I would go about that is thinking about it like this, where I know I've got the x squared differentiating to a multiple of x on the outside. That's the key thing I'm looking for. Does the interior function differentiate to what I've got on the outside? So I would imagine what I'm going to end up with. I know that sine must integrate to a minus cosine. So I expect to get some minus cosine of x squared from doing this. If I differentiate this, then the minus sign stays where it is for the moment. Minus cosine differentiates to sine, so I can get rid of that minus sign actually. The derivative of the inside comes outside, 2x, and the inside stays the same. So 2x sine of x squared. So actually this should be 1/2 or minus 1/2 cosine of x squared plus c. We could double check it if you like. Try differentiating that back. Does it get to this? The derivative of the inside comes outside, so 2x multiplies with minus 1/2, so you get minus x, and then the cosine differentiates to minus sine, which knocks out the minus sign. And we get back to what we started with. Now, some of these can be tricky, as I said. If you prefer, you can always do this by substitution and let u be the x squared and go through it that way. Okay? So we're kind of really getting into territory of going, well, they could be ones that you spot, that you can do by reversing the chain rule, but if you're unsure, just go through it by substitution and do it that way instead. Okay, so even though we've got to integration by parts and it felt like all of the previous stuff was done, there's still kind of like little caveats and things to look out for. Now the next thing to consider is it cyclic integration? So cyclic integration is essentially integration by parts with just a little added step to it. So the integral of e to the x sine x or the integral of e to the x cosine x are prime examples of this. These ones are rare. Okay, this is rare as a question at A-level maths, but it is integration by parts. It is at most doing it twice. So having had like the discussion with exam boards on this on social media, they feel that this is valid. This could potentially be a question. So integral of e to the x sine x, using your late rule, u is going to be equal to sine x, and dv by dx is e to the x. Okay, now I've got videos on cyclic integration and its process, so I'm not going to go through the whole thing, but the idea is that you go through this process and you do it twice, and it feels like you're not getting anywhere. It feels like you're going round and round and round in circles, hence cyclic integration. Okay, but you get to a point where you have the question e to the x sine x dx is equal to something plus something, take away the integral of e to the x sine x dx. And so what you can then do is add e to the x sine x dx to both sides. And then divide through by 2. So it's a pretty neat question. It's one that I met first of all in my first year of degree level, because if you keep cranking the handle of integration by parts, you're going to end up with e to the x sine x is the integral of e to the x sine x. Right, so you're going to prove that 1 is equal to 1. So if you've got to that stage, you've gone too far. Okay. So the next thing to look out for are partial fractions. So is it an expression where you can break it up into partial fractions? Of course, because these are fractions, the first thing you're probably going to look for is, does the bottom differentiate to a multiple of the top? And in each of these cases, you don't. Okay. So if we have this one, for example, then what you want to do is you want to rewrite that as something over x plus something over x plus 1. Okay, so break it into partial fractions. Likewise, for this one, we want to write that as the integral of a over x take away 3 plus b over 2x plus 1. Find the a and the b, and then integrate. This one, write it as a over x plus 2 plus b over x take away 1 plus c over x take away 4. Okay, find the a, b and c and then integrate. This one, 5x plus 2 over x plus 5 squared, x take away 3. So we want to write that as a over x plus 5. So you get a singular one, because of the squared in the denominator, you get a singular plus a double. Okay, so for the bracket that gets squared, you want one that has it to the power of 1, 1 to the power of 2, and then you've got c over x take away 3. So that's the format of the partial fractions there. Find a, b and c, then integrate. This one, similar vein, you've got x squared, so that's the integral of a over x plus b over x squared, so you want x to the 1, x to the 2, and then c over 3x plus 1. Okay? So in the majority, when you do the actual integration of it, because remember all of that's just finding the partial fractions, then you integrate, the majority of these is some constant over a linear term. So in each of those examples, okay, you've got a number over a linear term. This one, you've got a constant term over a quadratic term. So let's just make sure that we are happy with how you actually integrate each of those styles. So let's say we've got the integral of 3 over 2x plus 1. Let's actually change this. Let's change that to 6. Or let's say we've got 6 over 2x plus 1 squared. Okay, so both of these could be the results of having done some partial fractions. Now we're ready to integrate. Right, we're faced with this. If it's this, and this is the majority of the cases, you get this scenario, then it's a fraction. Does the bottom differentiate to the top? Not quite, but it is a multiple of it. So we're using this rule. And quite often we're going to be using this rule when we do partial fractions. So the bottom differentiates to 2. On the top you've got 6. So if we do 6 divided by 2, you get 3. So 3 times the natural logarithm of the modulus of 2x plus 1 plus c. Okay? Now, if we've got this one here, yes, you could do it by substitution. I don't know if you really want to kind of get into the habit of just using substitution for everything. 6 lots of 2x plus 1 to the minus 2. So let's rewrite it like that to start off with. Okay. Imagine that you are, imagine what the result's going to be. We know that it's going to be of the form 2x plus 1 to the minus 1. So if we differentiate this, the derivative of the inside comes outside, which is 2. Minus 1 comes down to the front, and we take 1 from the power. Okay, so we need to divide by minus 2. So minus a half times the 6 that we've already got there. So 6 times minus a half is minus 3. So we'll have minus 3, 2x plus 1 to the minus 1 plus c. Now you can double check that. Differentiate this back. The derivative of the inside is 2. So we'll have minus 6. The power comes down to the front, so we're going to have 6. Take 1 from the power, and we're back to that. So finally, is it an integral of sine squared or integral of cosine squared by themselves? In which case, we have to use double angle formulae. So, why do the other methods fail? So, everything that we've done in the past, we've got really two main things. We've got integration by substitution, integration by parts. When I say integration by substitution, that also includes all of reversing the chain rule, right? So, what do these look similar to? they look similar to maybe this one. Remember when we had cosine x sine to the 4x? It's kind of looking similar to that. But the issue is we can't reverse the chain rule because we don't have this format here. The interior function is sine x, because this is sine x all squared. But we don't have its derivative on the outside. We don't have cosine x out the front. So we can't reverse the chain rule on this. That's also why integration by substitution will fail. Is it integration by parts? You might be going, well, if we let the u be sine x and the dv by dx be sine x, what happens then? Well, what happens then, if we go down that route, du by dx would be cosine x, and v, so integrating sine x is minus cosine x. So we get minus sine x cosine x. Take away the integral of minus cosine squared. What you end up getting is something that just keeps on cancelling away. So you keep on getting this sine x cosine x, but they keep cancelling away. And the integral keeps on going round and round in circles. It looks and feels a little bit like cyclic integration, but there's no kind of like way of pausing it midway. Okay, so there's no kind of like stopgap there. So it kind of has similarities with things that we've seen, but unfortunately we can't really use those methods. So the double angle formulae. Cosine 2x can be written as 2 cosine squared minus 1, and it can also be written as 1 minus 2 sine squared. So cosine squared can be rearranged, add 1 to both sides, divide through by 2, to get 1/2 cosine 2x plus 1/2. So the cosine squared can be replaced with 1/2 cosine 2x plus 1/2. And then you just integrate that, because you've got a standard function, and then 1/2 integrates to 1/2 x. Okay, so you should be getting a quarter sine 2x. So a quarter sine 2x plus 1/2 x plus c. Now, cosine 2x is 1 minus 2 sine squared. So if we rearrange that, add the 2 sine squared to both sides, subtract cosine 2x, divide through by 2. So sine squared is 1/2 take away 1/2 cosine 2x. So this is 1/2 take away 1/2 cosine 2x. And then integrate that. So that's 1/2 x take away a quarter sine 2x plus c. Okay? And so sine squared, cosine squared, this is how you integrate them. If you've got these standalone terms, you must be thinking double angle formulae, rearrange, and then you'll get there. So well done if you've made it all the way through to the end of this video. I've tried to go through what I believe is everything that you need, but it is a convoluted issue. Differentiation is much more straightforward. Integration is complicated. There's lots of kind of caveats, there's lots of examples that look similar to one another, and you need to remember, oh, that's integration by parts, that's integration by substitution. You need to remember if you can reverse the chain rules, so little things to look out for. Keep an eye on what's in your formula booklet, okay? A number of things in the formula booklet, including some of these formulae, okay? The integration by parts formula, it's in the formula booklet, okay? So there are things there to help you, but there is no shortcut really. It comes through practice and the graft that comes with this. So if you think, oh, I'm just going to turn all of this into revision cards, that won't be the best way through. That won't be kind of the cure-all here. You need to sit down and go through lots of integration questions and try them out and just see where you get. There will be questions in the exam that will be use integration by substitution, or it will be one of those archetypal integration by parts, okay? It's only going to be some scenarios where you're going to have to choose which method to use, okay? And I expect that's probably going to be few and far between. But practice is the way that you get good at this.